Welcome back. Let us continue the discussion on this linear stability analysis. So, what we have done, we have already looked at different type of analysis, and we are going to look at two different kind of normal mode analysis here. One is the K-H instability, another is the with the viscosity, where we will come across or Sommerfeld equation. So, for K-H instability, we have taken situation and derived the linearized perturbation equation. So, this is the system that we have taken, and we defined all the characteristics of this particular system and other properties. Using that, for the inviscid case with e-rotation, we bring back our potential flow theory and got the Bernoulli equations. Now, for base flow, which is stationary and spatially uniform, except for that location where y equals to 0, there could be a jump. We get this equation, and the basic pressure varies with height. So, finally, we had a linearized equation for the disturbances. There are 4 equations, 2 equations from the mass conservation and the 2 equations from the momentum conservation. Now, to solve this problem, we need boundary conditions, and there are 3 different set of boundary conditions which is required. One is the zero velocity disturbance at y plus minus infinity, one is the kinematic condition, and another one is the dynamic interface condition, which says that when the surface tension is neglected, the normal stress must be continuous across the interface. Now, for inviscid flows, a continuous normal stress reduces to a continuous pressure across the interface. So, that essentially gives me this condition. Now, how do we get the solution for potential? Now, we have second order differential equation for mass conservation. So, which are del 2 phi 1 prime by del x 2 plus phi 1 prime by del y 2 equals to 0 to phi 2 prime by del x 2 prime by del y 2 equals to 0. Now, we have boundary conditions at infinity, which is limit y tends to plus minus infinity, that goes delta phi 1 2 equals to 0. Now, we have normal mode analysis, that means phi prime 1 2 would be f 1 2 y e to the power I k x minus omega t. So, that is how. Now, this equation, this reduces to del 2 f 1 2 by del y 2 minus k square f 1 2 equals to 0. So, the once this we put it back there, this is what now the solution what you can have, that is phi 1 prime equals to b1 e to the power ky I kx minus omega t, and phi 2 prime would be b2 e to the power minus ky e to the power I kx minus omega t. So, this is what we get for the solution of the potential. Now, we apply the second boundary condition. So, that is that kinematic interface condition. So, kinematic interface conditions gives us d eta by dt equals to v y equals to eta del phi prime by del y at y eta. So, this is my kinematic interface condition. Now, our tangential velocity essentially discontinuous. So, our tangential velocity across the interface is discontinuous. So, we get two set of equations, one limit y with increasing eta, that is del eta by del t plus u1 plus u1 prime del eta by del x equals to del phi 1 by del y, and second limit is y goes from the eta, del eta by del t u2 plus u2 prime del eta by del x equals to del phi 2 prime by del y. Now, cross terms can be neglected like this term or this term. So, these are the cross terms can be neglected after linearization. So, which get us I minus omega plus u1 k a equals to k b1 e to the power k eta, which is k b1. Similarly, I minus omega u2 k a equals to minus k b2 minus k eta, which is k b2. So, essentially this is my linearization. So, the linearization get me these two equations. Now, we will apply the third boundary condition, that is the dynamic interface condition, which says that at y eta p1 equals to p2. So, means at y eta rho 1 del plus u1 g eta rho 2 del T plus g eta. So, this is what we get. Now, from there we get I rho 1 plus u1 k b1 equals to rho 2 k b2 minus rho 1 rho 2 GA. So, my dynamic interface condition provides this. So, once we apply all these three boundary conditions, that means first the boundary condition at the infinity where y tends to plus minus infinity. So, you get these two solution. Then we put the kinematic interface condition, so that after linearization we get this, and then finally we get the dynamic interface condition, which after application get me this. So, now if we put the whole system of equation after applying the boundary condition in the linear system or in the matrix system, how the matrix would look like. So, we have an 3 by 3 system and the equations are for A1, B1 and B2, and if we look back, this is for A, B1, B2 coupled. So, once we do that, this is for A, B1 and B2, these are essentially, you can think about this is A x b. So, we are solving for A x equals to 0. So, you put things together, you get that particular situation, and the non-trivial solution is the, because of determinant of the matrix is 0. Now, if you look at the solution, so there is a quadratic equation for omega, which we solve with quadratic formula. So, that will get me rho 1 u1 rho 2 u2 by rho 1 plus rho 2 k plus minus 1 by rho 1 plus rho 2. So, which has minus rho 1 rho 2 k square u2 minus u1 square rho 1 plus rho 2 rho 1 minus rho 2 k g. So, this is an, one can think about it's an dispersion relation of omega k. Now, there would be, it's a quadratic solution. So, there could be two modes. Obviously, one is stable mode and the other one is unstable, which is greater than 0. Now, for that, this is unstable case. So, for unstable, k would be rho 1 minus rho 2 g u2 minus u1 square rho 1 plus rho 2 divided by rho 1 rho 2. So, which you that is lambda, that is my eta x t, this is state 2, this is state 1 rho 1 u1 u2, and this is my axis and this is my gravity. So, if we neglect the surface tension, then you can see what happens, that one can work out also. So, the solution which will tell you one stable mode, one unstable mode. Now, we can take some specific very specific case and see what happens. Now, first one, look at basic flow at rest. So, which means my u1, u2 these are 0. So, the two modes that we will get, that would be omega plus minus rho 1 minus rho 2 by rho 1 plus rho 2 kg. So, if you look at this picture where these are the basic flows and they are at rest, then we get these two modes. Now, if rho 1 greater than rho 2, that means this is rho 1 and this is rho 2. So, which tells that heavier fluid below lighter fluid, which is means the lighter fluid is top of that plate and heavier fluid is below, which is essentially an Norman flow characteristics, and that gives you an stable system, which nothing but my gravity wave. Other situation when rho 1 less than rho 2, that means lighter fluid is the bottom. So, this shows always unstable behavior. So, in this particular case where you see when the basic flow is at rest, the stability and the instability region can be identified in a. Now, the second case we can consider shear flow in homogeneous fluid. So, which will tell me that u1 not equals to u2 and rho 1 equals to rho 2. So, if you look at this, u1 not equals to u2 and rho 1 and rho 2 are same, because it is an homogeneous fluid. So, that gives me this condition, this is shear flow, that gives me this condition. So, my modes of that solution, the two modes should be omega is half of u1 plus u2 k plus minus I half of k. So, again this case is also one mode. So, always one mode is unstable and the growth factor would be growth factor is omega I equals to half of u2 minus u1 into k. So, that is my growth factor. So, one mode would be stable and another mode would be always unstable with growth factor to be like this. So, we can see some photographs of cage instability. So, there are two types of instability you can see. So, if there is a shear, so which essentially you can see here in the atmosphere, this is primary due to the gradient of the density. Now, in the jet also you see this cage instability, this could be due to velocity gradient, this could be due to density gradient, then there is a flow behind perforated plate. So, you can see the cage instabilities. There are nice picture of instabilities in cloud, smoke from cigarette. All these photographs actually show some sort of a cage instability. So, essentially if one would like to see these are this kind of instability we can see in regular life quite often. Whether we term that as cage instability or not, that is a different issue, but we get to see this kind of, because these are the pictures which you often see in. Now, we try to generalize cage stability analysis. So, if we try to generalize, we again assume one dimensional inviscid flow. So, the first thing we have small disturbances plus the normal mode analysis, that will give us ui prime equals to u, which is a function of y e to the power I k x minus c t, and second one would be p I prime equals to p hat y I k x minus c t. So, there is a nice theorem which is called square theorem, which says that disturbance propagating getting in direction of basic flow, in direction of basic flow is most unstable. That means the span wise direction can be ignored. So, the span wise direction can be neglected. So, we will get 2D disturbances. So, that will suffice the whole business. Now, if you write the linearize inviscid Navier-Stokes equation, which is some sort of an Euler equation, we will get du prime by dx plus dv prime by dy equals to 0, then del u prime by del t u del u prime by del x plus v prime del u by del y minus 1 by rho del p prime by del x, and the other component is del v prime by del t plus u del v prime by del x equals to minus 1 by rho del p prime by del y. So, these are the set of linearized equations. So, these are linearized inviscid NS equation. So, first one from continuity, other two from the momentum. So, generalize this Kh instability equation, where we again assume it is an 1D inviscid flow. So, we have a small disturbance, and the normal mode analysis we write like this: u1 prime equals to u1 and p1 prime, and also we assume that the disturbance is only in the direction of the basic flow, which will become more unstable, and so that we can neglect the span-wise direction and we get this equation in the linearized form. So, now we will see how we can obtain a solution for this particular form and this linearized system. So, we will stop here and continue in the next lecture.